Um, so I want to just try to say some things which are like hopefully not totally orthogonal to everything that's happened, but are kind of orthogonal to everything that's happened, and just explain a little bit what's going on. And in particular, if I put on my really corporate voice, by the end of this talk, you should learn why Whittaker coefficients are talked about in the subject, and also why we were doing the calculations that we did. Okay, so what I kind of want to start with is a little bit of a thought experiment as we try to figure out what geometric length is supposed to be, and not just as a conjecture that's like A equals B, but kind of unravel a little how is it supposed to work. So we start with an analogy with number theory. Yeah, and maybe for a while, I'm going to just take group G to be PG. So the analogy with number theory, okay, so in Gravere's talk, we all learned about real analytic modular forms. I'm going to talk a little bit more about holomorphic modular forms because I remember the one this one explained. So the analogy with number theory is like the following. So if you're given some sigma, a local system, so something like kind of representation in the Galois group of Q into SL2, which is the group G checked, and this should be a irreducible, and I'm just going to kind of ignore most things that have to do with Archimedean stuff because they don't matter to us. An irreducible, it's just completely an irreducible representation like this, then what does Langlands tell you to do? I mean, Langlands, okay, they tell you that you're supposed to define AP to be the trace of sigma. Oh, let me assume that this is everywhere ramified just to simplify. So they tell you that you're supposed to define numbers A sub P, which are the trace of sigma applied to the Frobenius element of P, where I remind you that there is the canonical conjugacy classes instead of this Galois. And hopefully also close. Then what you're supposed to do is you're supposed to write down Q equals E equals tau, and then you're supposed to write down power series at tau, which is tau, which is going to be the sum of an Q to the n, where you have the following basic properties. So if A0 is equal to 0, but this is saying that the constant term equals 0, and the word for it in philosophy, this is supposed to, well, this is called hospital. And this is supposed to match the fact that I said irreducible. So we're going to learn some of these words later today in the geometric context. I just want to put them on the boards that because this is an opportune moment to do so. The next coefficient I'm supposed to write is A1 is equal to 1. Amazing. Oh, and sort of wrote, well, AP is equal to AP. Sorry. This is the trace of sigma of the Frobenius elements. And an times am is going to equal an times m. I should have written those in another order. If n and m are co-prime. So now I just have to tell you what happens for powers of p. And in general, there's a recursion that says a p to the n plus 1 plus a p to the n minus 1 is equal to AP times a p to the n. And there's a factor I'm forgetting somewhere. It goes here. It's a p some power that like the weight of the modular form minus one, it doesn't matter. We're not talking about weights which are Euclidean phenomena. But every one of these might have a factor of p somewhere, but this and this is a recursion that tells you the value of a p to the n plus one, given a p to the n minus one, started with here, and a p to the n, we started with here. And then what the Langlands conjecture says in this very particular setup is that the resulting function f of tau defined on the this is just emphasize this is defined on the upper half plane is a modular form equal one. And this is sort of one direction of the Langlands program, but it's supposed to say something like essentially every modular plus something like essentially every modular form has this type. Which I'm being intentionally vague what that means. Maybe there are many things that aren't so well understood in arithmetic on the program formulation. And we're bumping into some of those, but I just want to give the flavor. Questions?
Some of this proved now?
Some of this, yeah, but that's not my, yeah. Yes, some of this is proved now. But that's not what I mean, in some sense, there's not really a definition of like what the relevant notion of Galois group is, and so you learn the kinds of substitutes. Anyway. So yeah, and you should imagine this Langlands program more generally is something like this for general reductive groups. So I just want to emphasize what happened here. We just started with the Galois representation. We wrote down the Q expansion for this putative modular form, and then someone was supposed to prove for you that this actually is a modular form, that it satisfies some kind of special functional equations. And moreover, like sort of like what you want to imagine is in general, if you have some kind of random Q series, this infinite sum of the shape, it's not going to have any special properties. But what you want to say is that if it's a modular form, it essentially comes by this construction. There's some kind of matching between this kind of arithmetic data, Galois representations, and this sort of world of automorphic forms. And that's supposed to be, there's many technicalities, but that should be roughly the shape of the Langlands program, something kind of extremely explicit. Now let's do this in geometry. And so imagine that I start with some local system, and it might be irreducible, but okay, let me this SL2. I'll just do it for general reductive groups for a second. And then what geometric Langlands in a baby form says that there exists some very nice eigensheaf called F sigma, which is supposed to be some sort of D-module sheaf on G. And what we want to do is we want to imagine sort of what this eigensheaf is supposed to look like. So the motto that we're going to try to characterize F sigma by its Q expansion. So, so here's the analogy. So the first thing is that there's this operation A0, from the modular forms theory. And this is going to correspond to, and here's number theory over here, like automorphic forms or modular forms over here. And here's sort of geometric setup over here. So this A0, so you can think this sort of map F goes to A0 of F in like modular forms to C. I'm going to change that in just a second. So the analogy says that that's like the functor we're going to learn later today. Constant term from D modules on bun G. I'm just going to start writing D to D modules on bun M, where M is a levy. We're going to learn about that later, but you can just have that in mind here. And there's something weird here, which is that this is C, and that's sort of some misleading thing. So this modular forms are really going to sort of constant functions on the positive plus. There's a subtle point in the passage from modular forms to automorphic forms, and this is much more quite thing. And so it happens to take some constant functions in. That's not true for the non-holomorphic modular forms that we were talking about. And so it's saying that A0 of F is equal to 0 is then analogous. This is my analogy expression here. This is analogous to saying that this F sigma is a customol for sigma irreducible. Again, I emphasize we haven't defined cuspidal yet. We will, but it's just get your brain primed for hearing the words later. Next, there was this. So yeah, I want to think part of what I'm trying to emphasize is like here you take this Q expansion and none of the Fourier coefficients are really distinguished. It feels very systematic. Like it's just A0, A1, A2, A3. And actually, from the perspective of automorphic forms, that's not the case. This A0 is really a different sort of beast from A1, A2, A3, A4. And so just a little bit primary brain for that. So now there's this A1 of F. And this is analogous to this operation of vacuum Whittaker coefficient. So I'll write quote 0. This is the vacuum Whittaker coefficient from D of bun G to vect. And now this condition that A1 of F is equal to 1 is going to get reflected in a condition that this coefficient of F sigma is just going to be like the object F sigma I want is going to be equipped with an isomorphism between its Whittaker coefficient and K. So I'm going to fix that once and for all. So this is what we call the Whittaker normalization. Yeah, and I guess I should say something about where this part of this analogy comes from. So a little bit of analogy between things like kind of usual harmonic analysis and geometry. Well, so sort of harmonic analysis using like real stuff, and then using modelic stuff, and then using geometry. Something you should kind of think you're doing is with harmonic analysis with R things, like maybe here you have the real numbers that gets turned into like kind of the Adels under the analogy, and then in geometry that gets turned into whatever it does. Well, so the Adels again, like in quotes. You have the integers inside of R, and that's going to be like sort of your global field inside of the Adels here. And this is sort of going to be something like the function field inside of here. And so when you see something like maybe G of R mod G of Z, maybe mod something like something else over here, like a maximal compact subgroup, this usually kind of gets transformed into from G on this side. And with this kind of thing in mind, I just emphasize that this A1 of F is like sort of draw the picture for a second, like here's the upper half plane. Everything's kind of periodic with period one. When you have modular forms, they're invariant with respect to translation by the right. And then what A1 of F is it's the integral of f of tau times e to the minus 2 pi I tau, d tau, along sort of R mod z, where this is one of these is my sort of copy of R mod z, was like this thing right here. And then what happens in our analogy is sort of R mod z gets replaced by the Adels mod q. I'm going to put here actually mod the integral Adels as well. And this is sort of this then gets transformed into this fun n in the case of, or sort of fun GA, which is fun n in the case of G being PGL2. And like then there's actually sort of a secret extra twist that comes up here, which is this omega that you realize if you just kind of think about the things a little bit more deeply. So I guess let's write the omega, I can't find totally talk quickly enough. And so now what we're doing is instead is we're taking this Whittaker coefficient, which is some kind of integral, meaning cohomology, over this fun n omega of sort of my sheaf. So this is sort of coefficient of some sheaf f. And then this is going to be times some sort of exponential. This exponential being this really being the restriction of the sheaf to fun n omega, and this really being the exponential sheaf as I defined it on Monday, and this integral really meaning cohomology. But very, very similar formula to here. Okay. Questions for a second?
Maybe like
Yeah.
apart from an analogy with the arithmetic, like is there another reason for phrasing the geometric Langlands conductor?
You mean like why did anyone do the geometric Langlands conductor to start? Okay, that's a historian question in some sense, a little bit historical question. I think very briefly, the story is that Langlands came up with these ideas about automorphic forms. Some folks in Russia, like Manin and Drinfeld, thought it would be very interesting to study this more in the case of function fields.
Right.
They sort of, Drinfeld really ran a big program of kind of understanding what was happening for PGL2, really by close analogy with the number theoretic situation. Some of these issues really beautifully go away, like what you mean by Galois groups, really understand in the case of function fields. And then Drinfeld started maybe to learn L-adic sheaves and started to use these kinds of methods in the theory, and really kind of like applied the sheaves functions correspondence to construct like an eigensheaf, basically by the sort of logic I'm explaining right now in some sense. And then the field developed from there. For example, people realized later that there were connections with like lots of things that were happening. The sort of demodular version of the story had connections with lots of exciting math that was coming out of the math physics world. And so that stimulated a lot of research. And also there's just, people kept finding beauty in the stuff. And so
Right. But here there's no kind of direct correspondence between the sheaf story and like functions. Or this thing.
You mean because of the demodule thing?
Yeah, I mean,
there's not a direct connection. There's like an indirect connection, which I can refer you to my recent paper with Dennis.
Okay.
Yeah. So, but let's take it as an analogy for a little bit. It's kind of it's a way of orienting yourself to what's going on. Like, at least for me, this idea of like thinking about a modular form in terms of its Q extension is extremely natural, and there's sort of like extra layers of abstraction that I want to unwind. why we're doing this Whittaker coefficient thing. Not necessarily getting to the question of why are we doing any of this at all. So. Other questions? Yeah.
So, that's quote zero, is there interpretation of the rest of?
Yes. Amazing question. I think Dennis has been planting questions in the audience, but this one I can still good, but I feel like we planted it. Yeah. Okay, so the other coefficients. So to keep going, so there's this AN. And so what we're gonna do is we're gonna take, okay. So first, if you have an integer greater than or equal to 1, then you're supposed to factor it. That was p to the r1 times p to the r1 ps to the s. This gives rise to a divisor on spec z, which is the sum of the ri pi. So this is a divisor, the effective divisor on spec z. And so the Whittaker coefficients for PGL2 are going to be indexed by effective divisors on the curve. So there's like some kind of exponentiation that's happening here, which is why A1 is like quote 0. Like you take 1 and you turn it into a divisor on spec z, by the way I just said, you get the 0 divisor. It's like just saying this because it's like the and you'll see people call it the first Whittaker coefficient and the 0th Whittaker coefficient in this subject. Related, now hence advocating the vacuum Whittaker coefficient. Done. You kind of confused.
Well, if you can't choose between 0 and 1.
Yeah, exactly.
You're like, I do.
Yeah, it's
So unambiguous.
favorite trouble. Okay, so so what is this Whittaker coefficient d in this case? So wasn't explicitly said. But it's some functor from d of 1 d to fact. And let me really emphasize it's going to be PGL2. And let me just say how it works. So I'm going to take bun PGL2. Here I'm going to take the set of all extensions. Well, which we can think of as some kind of twisted version of bun n, but now with the divisor over here. This maps to bun PGL2. Now this maps to H1 of omega of minus c. Like in my talk, we're taking the isomorphism, like the class of the extension, the isomorphism class of the extension. This maps to H1 of omega, and this is to A1, so say, again, like equating spaces and vector spaces. And I do exactly the same thing. I pull back tensor with sort of this exponential t. So this is psi e. We did difference and then we fall out. So in other words, I think kind of like what other versions of R mod Z could I have put there? I mean, like you see these twists, but they're really that's really just features of the global setting and what you're really kind of doing if you like, I'm not going to do this on the board, but if you work out this analogy between like bundles and adelic things, then what you're going to see is that you're integrating against characters of sort of this this group of adels mod Q, but they have possibly different conductors, and that's again like there's a sort of very precise dictionary between these two things, and that's the way that dictionary works. So the other Fourier coefficients, A2, A3, A4, A5, those all correspond to doing some integral against a character on the Sedelic quotient in this world, but an integral against a character that has non-trivial conductors. And that sort of exactly perfectly matches what's going on here if you work out the story. But if you don't want to work out the story, just believe me about it. And if you want to work out the story, it's like
Interesting something. Yeah, I was going to say that maybe it's worth noting that these are literally all the non-constant Fourier coefficients. So whenever you consider extensions of a line bundle by a line bundle, the extensions are parameterized by a vector space. So you get a map from a vector space to bund, in this case, bund PGL2. And when you have a vector space, you can try computing Fourier coefficients on this vector space. And all the non-zero ones are captured by this unstart.
okay, so now okay, so let's keep going with the analogy. So again, I was supposed to have this sort of modular form, and again we have these sorts of properties that an was given by some procedure. I'm not gonna review it a second at this moment, but now let me tell you what the analogy is. Oh, wait, Robert, did I answer your question? Okay, so the analogy now is going to be that this, if I take this d Fourier coefficient of this half sigma, and here I remind that sigma is going to be a local system for SL2. So in other words, it's like a vector bundle with connection of dimension 2, and it has some determinant stuff that we can find. So what's going to happen here? So here I'm going to write my d as some kind of sum ni xi. And when you write down this coefficient of this f sigma, what you're going to do is you're going to take sigma at each point xi, you're going to tensor it with itself ni many times, and then you take the tensor product over all of these i's. So this is just a fiber of this local system sigma at this point. So again, maybe I should emphasize at some point, so numbers turn into vector spaces under the language between like geometry and number theory. This is like clearly a very flimsy formula because I just said for every divisor, like there's some isomorphism, two vector spaces, like yeah, it's not totally convincing, but let's believe me for a second that this is an important formula. Questions?
Just to clarify with for the annual group, somehow the C square, the rule will come in.
Amazing, exactly. That I could have planted the question again. Exactly the next thing I wanted to say. So now what's happening for general G is going to be the following. So the Whittaker coefficients are, and I'm going to say naively at this moment because we're going to improve this later. But we're at the same naive level now. They're indexed by divisors p on x, but valued in dominant colates. So in other words, these are going to be sums that look like lambda I xi, maybe I'll just put xi. Where each of these lambda i's are dominant colates. You do exactly the same thing. So you take some von n, and instead of putting an omega here, you put an omega of minus d, and this will map to von g, and this will also map to a1, and the fact that it maps to a1 is going to be exact. Well, this is going to map to a product. The way this is rigged, this will map to a product of h1s of omega of well, the alpha I applied to my divisor. You're right that this is minus my divisor. And this will map to a product of H1s of omega, which will then map to H1 of omega by the sum map. And this is my A1. So I'm saying this quickly, you should just sort of maybe believe me that it works. It's just if people want to play with the combinatorics, I'm just trying to say that this dominance condition is exactly the statement that each of the divisors that occur here is effective or minus effective.
I was just wondering, is this formula using the fact that sigma is, so if the SOT piece is using the fact that you have a local system and not just a vector bundle?
Not so far, but you might have imagined the following, like maybe I worked with analytic sheaves. I never used D modules in this setup so far, right? Like I just said D modules, but I could have done any other sheaf theory I wanted. The discussion would go through fine. So but
Sam, can you push the other board up a bit?
good. Yeah, and let me just say, I guess just to conclude this thought, now what's happening for general reductive groups is that if I take this coef D of my F sigma, the generalization of the oh no, I wrote the formula wrong for spin Ni of sigma. So. Okay, so the corresponding formula here is that it's going to be the tensor product over these i's of so here my d, let's say I write it as lambda I xi. I'm going to take this v lambda I like twisted by sigma, but the fiber of sigma at this point xi. So what I do is so associated to this G-check local system, and a co-weight, in other words, a weight of G, like I can form this representation of G-check. I can form this representation of G-check. Now I can use sigma to turn that into a sort of honest local system of some rank on my curve, and then I'll take the fiber of that at the point xi, and then I'll tensor over these i's.
Can you recover the extras from all possible coefficients and integrating over all these?
Oh my god, it's like every. I'll come back to that. Okay. Okay. So that's what happens. So I want to say, like, whatever geometric length is, I'm looking for some kind of object on sigma for each local system that at least has like this kind of property. Maybe, I mean, definitely in a smarter sense, but we have like some idea of what shape of thing we want. And moreover, we want it to be sort of essentially uniquely characterized by that. Okay, so now there's sort of a problem, which is like, okay, this F sigma, again, maybe the people tell us that she's something roughly like an irreducible reverse sheaf. Like, if you just think this is clearly too weak of a condition to uniquely characterize some kind of irreducible reverse sheaf. Just like a bunch of, there's not enough geometry. So what we need is smarter versions of Whittaker coefficients. That have sort of more geometry. So in other words, one of the differences with number theory is in number theory, as best we know, prime numbers are very static objects. Can't like wiggle 5 into 7 or something, no matter how hard you try. But in geometry, you can move one point into another, and so there's this sort of built-in geometry on the indexing sets. And what we're going to try and do is sort of improve those. So, so the first thing, so there's sort of an easy upgrade. Which is going to be the following. So let's say, for simplicity, my group was PGL2. Then for every divisor, for every integer d greater than or equal to 0, I sort of can easily just vary the definition, and I'll define some functor coFD from this category of D modules on bun G to the category of D modules on the symmetric power of the curve, which is the space of divisors d greater than or equal to 0 of degree equal to D. And this is rigged so that for every divisor, if I take the discrete fiber at D to go to that, this is going to be my earlier coFD. So I can sort of take all divisors of a given degree and glue the corresponding coefficient functors into a single coefficient functor. So that gives me some geometry, and I can adapt the above. So it can easily adapt the above to say what coFD of F sigma is. Well, at least pretty easily. But this is like starting to get, in the case of PGL2, this is really starting to get towards what people call the Limon sheaf. If you've seen those the words before, if you haven't seen. But maybe just believe me about that. That basically there's this kind of like very easy thing that you can do, which is to just adapt the whole story to allow you to vary the divisor within a family, like of course fixing the degree of the divisor. But I think that makes sense. Now, there's sort of a real problem, which is, so what did I do now? Let's say, like, again, maybe PGL2. There's a real problem, which is that now, like, what's the best thing I can do out of this data? I can take some product of categories of D modules on all these symmetric powers of the curve, and I get some kind of Whittaker coefficient functor. And this can't possibly be fully faithful. It can't be anywhere near fully faithful. In other words, what I'm trying to say is like, in number theory, okay, at least for cuspidal modular form, you can completely recover it from its Q expansion. That's just like, that's like complete tautology. Or I mean, it's Fourier theory. But there's like nothing interesting that's happening here. But here, there can't really be a fully faithful functor, which would be the statement that if you started with a D module here, again, maybe cuspidal, like saying that this is fully faithful means that you can recover it from its essential image here, right? That's what you would want to say. Say like, I can take some kind of, let's say, cuspidal automorphic sheaf and just completely recover it from its Fourier expansion. And that's the relation of this DCD. So that actually, so wouldn't that be an effect? No, because this thing, so this, you should think of this as something like a set of modular forms. Yeah. And you should think of this as something like the set of Q extensions. At least that's what we're trying to get at. It's like the set of all possible power states that we're written down. and so in other words, you're trying to characterize the essential image, you're trying to say like what happens, which is a separate question. We'll come to in a moment, but like injectivity is just like you can cover the outcomes you mentioned. Okay, that's all. Good. Yes. Other questions? Objections? Okay, so this couldn't possibly have been fully capable, and let me just briefly say why. Like, this is a product of infinitely many things, and this category doesn't have that many idempotencies on it. That's like sort of many idempotencies. Like there are two connected components here. There's infinitely many components here, and
Are you using PGO2 here or?
am I using PGL2?
Yeah.
I'm sort of using the fact that it's an adjunct group to slightly simplify some things psychologically. I would say that. Or at least there's.
Sam,
But it's cosmetic.
if I replace PGL2 by GM, do I easily see that functor is not fully faithful?
No, in the case of let me like that's exactly I sort of want to stick to semi-simple groups, but like okay. I'll just briefly say like here the question is what's gonna happen if you take GM here? And if you take GM, let me just say you'll get kind of confused because I said these Whittaker coefficients are supposed to be parameterized by divisors valued in dominant co-weights. For GM, dominant co-weights means the integers. And so what we're talking about is just the moduli space of all divisors. And like that's confusing. The moduli space of effective divisors is great. The moduli space of all divisors is like something exotic that was defined by Dennis in the 2000s, which is like. And so it exists, you can say the words, but it's I want to keep it orthogonal to the discussion. Okay. But it's a great instinct to test these things on in the GM case. So there's a fix, which is that there's this sort of ultimate coefficient functor that goes from the category of D modules on Bun-G into left G checks on. Exactly. So let me just again sort of comment. How do you think about an object here? So like for me, objects here are kind of like little moving pictures where I have like a bunch of maybe V lambdas or direct sums of V lambdas sitting at different points. And they're allowed to come together as like tensor products, but that's like the kind of thing that's an object of this category. This category then doesn't want me to say that it's self-dual, which means you can also think about pictures like this giving you functors into facts. And the corresponding functors in this picture is going to be that coef functor that I talked about before. This or
You say just a little bit about the symmetric power there and one space not really having multiplicity or where
like this symmetric power. This symmetric power is coming up because it's this business. So here there's this V lambda I that came in, this highest weight representation of the reductive group. In the case of SL2, there's like the standard representation, which is sort of when this lambda is like 1, and when this lambda is 17, you take the 17th symmetric power of the standard representation.
Okay.
And so that's where this like sim 17 came from.
Ah.
Yeah.
Oh.
Yeah, and this rhyme space doesn't have multiplicities, but if you sort of track these as divisor, and if you really think about the representation and like you only look at some portion of it, then yeah, you'll see geometry as much as how it's something.
when it's that when I collide points I get lambda 1 tensor lambda 2 or that
Yes.
and in the SL2 case I add numbers and that translates to symmetric powers.
Yeah, I mean, you get this tensor product, which is sort of that thing, but then modulo order terms. Okay, you should think about sort of the category with some portion of the stuff that you check on. It's going to be this data on the symmetric power. So with the leading order, then we'll do lambda 1 plus lambda 2, and the rest will go with the quotient.
We get some sort of branch here coming up, is it the new world curves?
Yeah, branching, yeah, exactly, like the multiplicities, and yeah, that's great. Okay, so then, so let me sort of. Okay. Now I said this, and so what we did is you should think what this did, like you don't have to like necessarily like what you really have to know is this functor, but what you should maybe feel just for navigating it is it's something which kind of glues together all of these more naive Whittaker coefficient functors. When we say the definition of this coef is it's more subtle. So what you really kind of do is you go to this d of 1g. So this maps to this Whit star of g over this Ron space, and then you say that this is equivalent to this g check Ron via this Castleman-Floyd formula. Which uses the connection between G check Ron and the Satake category to just sort of put these two things on equal footing. So that's like a little bit the intellectual development that happened so far. And it's like I don't really know any way to just sort of say in the same sort of simple terms I said before exactly what this coefficient functor is, because rep G check Ron isn't just d modules on some space of divisors, it's its own.
Just clarify that if you like evaluate it point-wise, we'll probably get this construction.
That is correct. Yeah, if you evaluate it point-wise, you get the previous construction. If you do this divisors, you get the previous construction. That's completely correct. And the subtle part is both defining sort of how those functors glue together as you vary the degree of the divisor. Like you want to stick them together into one place. That is absolutely the subtlety, and that is what took people some thought in order to figure out this.
And also, did someone say in an earlier talk that the adjoint to this functor is something that was coefficient functor in what's it described?
Yes, so there's a left adjoint which is this Poincare series operation. And you can think of that as just like doing this rep G check Ron also acts on G of bun G, and you can think of it as just acting on that thing I called the Poincare sheath. Well, that's what it is.
Something.
Yeah.
Is there a number theory analog of this Poincare series? By the name of it, there should be question.
Yes.
Indeed.
It's like you can look it up on Wikipedia. It's the Poincare series. It's the thing which is adjoint in the sense of like vector spaces to the operation of taking Whittaker functions. So it's like basically you should think of it as some automorphic function or some modular function that when you do the dot product against it, it just computes the. Other questions? Cool. Okay, so now what happens? So secretly what happened secretly in my talk on Monday is that we had the following picture. So I just explained that there's this Whittaker coefficient functor to rep G check Ron, but who wants to say rep G check Ron? That's like it's a little bit scary the first time you see it, so we didn't say that on Monday, and Andreas introduced, no, we did say it on Monday, but we didn't say this Whit star or G stuff. So we didn't quite say it in these terms. But there's this gamma lobsis check, which maps by this gamma spec to this rep check run. And Dima stated that this was fully faithful, or I stated that this was fully faithful, maybe. And there was a statement that this functor of LG that there exists this functor that we now call LG course, which goes from G modules on Bungie into this subcategory of global nature. And then there's this renormalization procedure to get LG and this assertion that it's essentially an equivalence. But in particular, that's telling you this functor from D of Bungie into rep G check run a posteriori, the theorem says is fully faithful. Up to this non-tempered things. So specifically, if you work with this tempered quotient of D of Bungie, the resulting functor is fully faithful. In some sense, that is the last theorem that gets proved in the development of the subject. For general reductive proofs, Fourier theory is much more subtle and there's not a clear roadmap for what sort of things you're supposed to try to do. For PGL2, assertions of this type were like kind of proved in some form in the work of Frenkel, Gatesbury, and Valonen. I mean, they did GLN, and for GLN, similar sort of things were considered in kind of this exact setup by Dario Beraldo. What? No, for GLN, the fully faithfulness with the assertions on the classical category were proved by Dario. But the part of the hard part for the theorem is figuring out how that Fourier theory is supposed to work for general reductive proofs. That works. In other words, that you can recover a D module, at least a classical one, from this kind of, again, this is some version of like taking you to extension. Okay, so that's why the geometric Langlands functor was defined the way it was. I want to move on to something slightly different for a second. Yeah.
Should that Rand be a Van Newell or should it not be a Van Newell or? One sentence answer is fine.
Yeah, so it doesn't make a difference because Ron Newell is like a full subcategory of so. I mean, like there's, or you mean this Ron?
Yeah.
Well, it also doesn't make a difference. You can do it. There's a lot of flexibility around those kinds of things due to the contractibility of the routes. It's essentially and once you do some version of Ron, you'll get the right thing because all of these are like this just full subcategories. So yeah.
Why do you get fully faithfulness? I mean, the Langlands is an equivalent, but there was this quotient, right?
There's this quotient, so it's not fully faithful, and that's just like that's like the following principle. So I said modular form you can recover from its Q expansion, but these Whittaker coefficients only remember A1, A2, A3, A4, A5, and the constant function 1, which is a perfectly valid modular form, is annihilated by if you only remember A1, A2, A3, A4, and you don't remember A0, then you don't know about the constant function 1.
Okay.
In other words, that gets annihilated by those operators. And so, yeah, that's why I keep saying it's essentially fully faithful, not actually fully faithful.
Okay.
Is what actually, there's some, let me just say some true theorems, which are that if you take this D of Bungie hospital, this is contained inside of D of Bungie tempered, and this is contained, again, theorem, big theorem is that this is contained inside of this rep G check bond. So those are the true theorems. So there is a kernel, and for example, the constant function, the constant sheaf is going to, for non-abelian groups, will be annihilated by this operation of taking Whittaker coefficients, just like for PGL2, the constant function was annihilated by all the Whittaker.
Sorry,
if P bungee cusp is contained in theorem. But how about
Well,
There's a first conclusion.
yeah, Vegas on that is
It's a
fine.
reference to what.
ah,
It's capitalized people.
There's a first conclusion. Continues on the first line.
What was that?
The first line is.
Along it, not be red, what's that? Along it, not be.
That's right, so that was what I called for during that talk. So there's sort of competing notation in this business. So this is what we've been calling COLA since that talk with that. So Monday's functor got renamed to COLA 0 or COLA that. So, and I did a mortal sin on Monday, and I used notation that was going to be competing with notations later that week. So, yeah. But now you should take this as the official definition of COA. It's the thing on this. So yeah, so one of the big problems that you try to I guess I'm not that the geometric Langlands conjecture is addressing is you can think of it as just the statement that you can recover a non-morphic sheet under some hypotheses, which shows the subtlety of the problem a little bit from its Q extension. What's else? The
Hugo plus master object.
Yeah. 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 The actual D of bungee is this internal and that's related to the fact again that taking the Q expansions of say kills some objects. This is precise measure of what's happening now. Okay, so I just want to say kind of I said something about so I want to say a little bit about what happened yesterday. So I stated, and then it's kind of an exercise from what was explained in the afternoon yesterday. The valence and Drinfeld theorem that functions on these operas on X act on this sheaf of critically twisted differential operators. As a D module on G. And then for sigma and oper, defined this F sigma following valence and Drinfeld as this quotient by some maximal ideal. What happened yesterday and what's also about to happen later this morning. So now the big goal that we're like about to complete is the following. So it's a commutative diagram. Let me just remind of the following form. So there was this localization to the G of bungee. Then there was this Langlands functor into this intro Nope, of Wilkes G check. Now, this was equivalent by the FLE to this Intco star on these monodromic free operas. And then there's the spectral Poincare series that Kevin talked about. But the idea being that like Whittaker things have something to do with the cosine section, and operas have something to do with the cosine section. And so we think of this, it's a very precise analogy, but we think of this as kind of a spectral counterpart to that construction of Poincare series from automorphic forms. So the big goal was this, and Nick will explain it more in his talk. Let me just kind of say what's going on. So this LG, I mean, okay, there was a further part of this diagram, like where this was this functor of taking Whittaker coefficients, collapsed a triangle into a line, and
See the bottom line.
Will you also please take off the back?
take off what?
The that on the table. Back.
Oh, yeah. Okay, so kind of what is this saying? So this sheaf of differential operators is the localization of the vacuum representation, thought of as a factorization algebra living on this whole Ron space thing. I'm just going to write it this way. And now what we're doing is we're computing coef of this diff crit in this commutative diagram. And what are we saying it is? So we're saying, okay, you're supposed to take the FLE and apply it to this vacuum representation, and then do this spectral Poincare series to it, and then maybe even do some kind of like gamma that global section. Some kind of global sections. See, I'm actually just gonna do it in one shot. Let's just do this LG. I said coef, and it's something more. You're saying something more refined with this diagram. So we're saying where does this diff crit go under the Langlands functor? So this diagram says it goes here, and now this is points back. So the basic property of the FLE was that it sent the vacuum representation to this guy Z, these functions on regular operas. And the basic property of the spectral Poincare series is that this maps this to the structure sheaf of global operas. Thought of as a quasi-coherent sheaf on Wilkes G check, and therefore they live irreducible. They're all irreducible local systems, so this info versus quasi-co doesn't enter in there. But this functor factors through this okay, but it was to sheets anyway. So that's telling you the kind of the So now, what basically the work from yesterday is going to imply that this LG of F sigma, if you think about what that's saying when you quotient by this ideal, you're just getting the skyscraper sheaf at that point. So this is equal to the skyscraper at the point sigma in the space of operas. So the operas on X, we emphasize. And that's really, this is basically my formula for what F sigma is. So in other words, F sigma has the right Whittaker coefficients. So I guess I wrote an explicit formula before for what I think the Whittaker coefficients of this F sigma should be. And if you think a little bit about, if you unwind the abstraction, that's really just saying that kind of it looks like this gamma of the skyscraper sheaf with that points. So that's kind of just okay. That was my attempt to take what's happened and try to give people a feeling a little bit further. things are. So that's my summary.